Okay. So welcome back everybody to the nextPYP workshop. Now we're going to switch gears a bit and move on to session 3, where I'm first going to talk about on-the-fly data pre-processing, and then I'm going to hand it off to Ye for the last session of the day, where he's going to talk about some advanced topics. Okay. So moving on to the live pre-processing of tilt series. To give a brief overview of what I'm going to talk about in this session, I'm going to introduce why you might want to do live data pre-processing and some challenges that are associated, in particular with doing all of these pre-processing tasks on data as it's coming in. Then I'm going to introduce the notion of a session and how you might want to manage the sessions within your nextPYP instance. So this includes things like how to start a streaming session and as well how to navigate around the different features in the session. I'm also going to talk a bit about account and permissions management because it's a bit different for live streaming sessions as it is for your regular projects. Then I'm going to get into the nitty-gritty of how sessions actually work. So how files are transferred from your microscope onto your computational system and how the data pre-processing jobs are launched after you have this data available. I'm going to touch briefly on how we support high throughput acquisition and a bit about like how this job is done. So I'm going to introduce the notion of daemons for doing this like continual file transfer monitoring and the launching of jobs. And I'm going to introduce the features on our website that allow you to monitor your data quality as results are coming in. I'm going to talk about how like the resource allocation in terms of the compute resources are managed to allow users to do this live processing of large volumes of data. And then I'm going to talk about how you can filter the results that you get, export them either to like external programs or to the actual project's part of PYP. And yeah, I'm going to run through a brief demo of how you might do that like export import process. Okay, so why is live data pre-processing important? So nowadays, as Alberto talked about in the very first session, many high throughput data acquisition methods exist for Cryo-ET. And in these sessions, you can generate up to terabytes of data, so a large volume of data. On the other hand, if you have corrupted projection images, then this can invalidate an entire tilt series worth of data. And, it takes a long time for this data to be generated, and these are like not simple preparation processes. So you want to help ensure data integrity as much as possible. And the best way to ensure that is to make sure that the data that you're gathering is good quality. So on-the-fly analysis of your tilt series data can help you to ensure that your data is to standards. Obviously, having these results displayed quickly is very important in making this decision. So we allow the fast and real-time streaming of the results to our web GUI or graphical user interface. So working with live data does present some unique challenges. Basically, the challenges boil down to the fact that working with tilt series is harder than working with 2D projection images. So in tomography, the tilt series is like your basic unit of data, you can think of it as. So if something goes wrong when you're collecting the tilt series, then you can't really do any downstream processing. So when we're dealing with data that's coming in live, it's hard to tell whether the data collection has finished or if the process simply failed. And so you need to continuously monitor for new data. And if there is data available, you need to transfer that data from your microscope to wherever you're doing your pre-processing. Next, there's a problem of tracking your tilt series images. So there might be cases where tracking just like fails across the board and you can't use that tilt series data. Other methods, like especially with high throughput acquisition methods, there is no tracking. And by doing the alignment of your tilt series data on the fly can help you determine whether your tracking procedures are proceeding as expected. Next, you might have images that are blank or have contaminants like ice and like other undesirable particles. And it's good to have an idea of like which tilt images have these contaminants so that you can like exclude them or you can like regather data from the areas that aren't necessarily good for imaging. There's also problems that are associated with fibromela, namely high beam induced motion. And at high tilt angles, like you might get more motion. So if you process data that's gathered using fibromelas, then you might want to exclude these images or these regions for downstream analysis. Lastly, like I mentioned earlier, with these high throughput methods, you can get lots of data coming through at once. So just being able to wrangle that volume of data is in and of itself a challenge. So this is briefly kind of like a high level overview of how the live streaming session works. So starting from the top left, you have your microscope. Using some like acquisition methods such as beam image shift, you can get your raw tilt series. In this case, I'm showing like 25 just as an example. You want to transfer those tilt series from the microscope to wherever you're doing your computation. So that file transfer will result in the 25 tilt series being available on our shared network storage location. And then from that network, you can launch jobs to do the pre-processing tasks, deal with your data and get your results. And those results will be streamed in real time to the nextPYP website, which is like continuously updated so you can monitor how your data acquisition is going and how your data is looking. So this is how you would start a streaming session. Starting with the image at the top, instead of creating a new project, we want to navigate to the sessions page. So this is indicated by the red box here. If we click on the red box, it will bring up this page where you can start either a single particle session or you can start a tomography session. For the purpose of this presentation, I'm going to talk about the tomography sessions and how those work. So yeah, the sessions page, the landing page looks like this. You'll see Jeff briefly introduced this in his presentation, but you'll see like the different icons that you can use to interact with the sessions, the type of session that you've launched. You can give your session a name, which groups that the session can be read by, and some stats about your data. So in the session management on the very far left pane, you'll see there's 4 different icons. So there's this I, which represents opening a session, copying a session. So if you want to make like another copy of your session to play around with some of the parameters, you can do that with this button. You can also delete sessions, or you can show your file system locations. So if I were to click on open session, it would take me to this page where I can enter in the different settings for my session, such as the raw data, gain reference, microscope parameters, basically the things that I would want to set for my pre-processing jobs. If I click copy session, if I click copy session, it would bring up this window where I can give my copy a name. So for example, I made a copy of a membrane protein data set and I called it pretty fittingly membrane protein copy. If I want to delete a session, it will bring up this page, which gives me a warning saying that if I delete the session, then all of the raw data would be deleted if I select the option to move the raw data. I will elaborate more on like the different ways that you can transfer the raw data, but for now, this is what the window would look like, and then you can confirm or deny your actions. Lastly, if I click on show file system settings, it will bring up this window with the like network path here. And I can click copy to copy this to my clipboard and then like go into like the terminal, for example, and navigate to the file system locations. Okay, so starting a streaming session, if I click that eye icon, it will open up a page that looks like this. The very first time I open it, all of the parameters will be blank and I'll have to fill them in. So the session page is really where the central navigation occurs for how you want to control your data processing parameters and your compute resources. Okay, so I'm going to talk a bit now about the different kinds of access management that we support in creating a session. Jeff briefly talked about this, but the main difference here between like sessions and projects is that access is granted on a per group basis. So let's say, for example, I have this group up here of 5 users, as well as an administrator. My users can belong to different groups. So for example, I have the hat group here, as well as the no hat group here. And what this means essentially is that users within one group can have read access to their sessions. So for example, if the astronaut creates a session to analyze some data, then the painter and the detective will be able to read the astronaut's sessions. On the other hand, the person with the laptop and the scientist won't be able to read the astronaut's sessions. And same thing with the no hat group. If the scientist makes a session, it can be read by the person with the laptop, but not by the detective, the artist, or the astronaut. On the other hand, all of the users in a lab might belong to one lab group. So everyone in this group will have access to everyone else's sessions and they can read them as such. You can control the session permission or the user permissions and which group they belong to if you're the admin. These are just some screenshots of what the admin tab might look like if you are such a user. Okay, so one of the motivating questions for coming up with live data processing is how can you get quality feedback from your samples given resource constraints? So for example, now we have packages such as Bisect that enable the collection of a lot of data from multiple regions in the micrograph in parallel. So you might, in one capture, you might be able to capture 25 different tilt series, for example. And how can I best process all of that data and get the results as quickly as I can? The answer to this is to exploit this idea of weak scaling. So in the live sessions, we allow for the fine-grained resource allocation, which can afford flexibility and job parallelization. So what I mean by this is, let's say I have 100 cores. I can decide how I want to allocate resources for those 100 cores. So for instance, I might want to have one core per tilt series. And in that case, I can process 100 tilt series at the same time and get the results for those 100 tilt series very quickly. And then the users can define how they want to allocate these resources on a per tilt series basis. So you'll see it's a very flexible system in terms of how quickly you want results to be generated. Okay, so there are some options on the Sessions Operations tab that let you monitor how your system is performing under the hood. Because we are dealing with these large amounts of data, it's important to keep track of things like storage and making sure that you're not exceeding what the storage limits of your file system are. So here, for example, you can see the different mounted file systems, as well as the type of system it is, the total storage that you have, and then how much of it is left and what percentage of it is used. You can also keep track of things like the transfer speed of your files. So in the graph on the top, each of these red dots represents the transfer speed of one file, so like one tilt series, for example. And then the red or the black line will represent your average file transfer speed. You can monitor the status of each of your individual file transfers in the plot on the bottom. So this will list out each of the files that are being transferred or have already been transferred, as well as the progress. So in this case, these two are finished being transferred, and this one is still waiting to be transferred. And at the top, you have a nice summary of, oh, I have 7 files that have finished being transferred and 3 that are currently in the process of being sent. Okay, so the file transfer daemon is actually how these files get sent. So the way that this works is that whenever it detects a new tilt or a tilt movie is available, it will transfer the file to the shared storage. So the settings for this is controlled under the session settings tab on your settings page. You can set things like how long you want the job to run for, whether or not you want to transfer any additional files. So here, let's say you have some ndoc files containing extra metadata. You can click this option here and then specify the file extensions that you want to transfer to tell the daemon that, oh, in addition to my raw data files, I have these other files that you should copy over that would help facilitate this kind of pre-processing tasks. So some files that you might want to include here include the raw tilt files, order files, mdoc files, stuff like that. You can also specify how you want to transfer your data. So there are 3 options. It will bring up a list if you click this window. So you have move, copy, and link. Just briefly explaining what each of these different options do. So the move option will copy the raw data from your original location. So let's say the microscope to your session location on the cluster, for example, and delete the original data at its source. So this is the most commonly used form that we have for file transfers. The other option is copy, which does basically the same thing as move, except it will keep the original data at the source location. So essentially you have 2 different copies of your data. The last option that we have is linking, where essentially instead of copying the files, you'll create a soft link from the original location to your like cluster network location. This option is mainly used for testing purposes because it's more lightweight. So you can like test out things and debug without having to take up storage space. Okay, and you can control the launch of your different daemons through this operations tab. So you'll see that there are 2 daemons available for tomography. This third one is for single particle analysis. So I'm going to talk about the file transfer daemon first. This is, again, the file transfer daemon. So you'll notice that you have all these different options. So you have from left to right, the daemon name, the status, like whether or not it's running. You'll have the start button that controls whether this daemon should start. You have the stop button to stop this daemon, or you have the cancel button to stop all daemons. You'll notice the cancel button is only available for the top level job because it makes sense that if I want to cancel all of the jobs in a tree, I should start from the one that is at the highest level. Lastly, there's this logs button that can display the output from this file transfer daemon as either it's being coming in, so like from, let's say, your console or from standard out, or it will like keep track of any output that's written by any of the jobs spawned by this daemon. So the logs button is really helpful for displaying things if you want to debug why your session went wrong. The second daemon that we have is this data preprocessing daemon. So again, you have the name on the left, the status in the second column. Here you'll see there's 2 different options under controls. So we have restart and clear. Now the difference between these 2 relate to like which jobs you want to restart. So the restart button will only restart preprocessing steps that come after the step that was changed. So for example, let's say I'm processing this purified ribosome data set, and I set the particle radius to be 80 angstroms, for example, and I pick 8,000 particles. And I go and I look at my particles and I realize, oh, well, the particles that I picked aren't really that great quality. So let's increase the radius of my particles for detection and then rerun the job. So I can go into my settings, change the particle radius from 80 angstroms to 90 angstroms, and then rerun my jobs. Intuitively, I don't need to redo the tilt series alignment, the CTF estimation, stuff like that. I only need to like repick my particles. So if I click restart, the restart option won't do any of won't recalculate my tilt series alignment. It won't recalculate my CTF estimation. It will only run the things that come downstream of particle picking, including particle picking itself. Now, on the other hand, let's say I completely messed up my tilt series alignment, my tilts don't look great at all. Then in that case, it makes sense that I would want to restart everything from scratch. So this is when I would use the clear option. So clear will restart all of my preprocessing steps. So one of the kind of things to keep in mind for the live data preprocessing is how can I get results quickly while ensuring the same accuracy as offline preprocessing? So to start, we need something to work with. We need our raw data. You'll input the location or the path to your raw data under the raw data tab. So this accepts the same file types and formats as traditional preprocessing that Abby talked about this morning. So some options here might include TIFF files, MRC files, EER files. And then from the output of my preprocessing, I will have a tomogram that's been reconstructed for each tilt series. So it's nice to note that all preprocessing tasks can be done live. So the tasks like frame alignment, tilt series alignment, CTF estimation, tomogram reconstruction, or tomogram denoising through external packages, and particle picking, all of these things can be done live. Some caveats do exist. So you could do manual particle picking live, but it would be very hard to keep track of, or to do manual particle picking as your data is coming in. You can imagine your data is coming in pretty quickly, and it might be hard for you to keep track and stay on top of data as it's coming in and pick particles as they come in. It also wouldn't really be the best choice to train a machine learning network while you're running a live session. So you can certainly do it, but the time that it would take to train the network would be much, much slower than the time that it takes to actually run the live preprocessing. But if you do have a trained model, you can use that trained model here. And the other one thing I want to emphasize about the live session is that it's really a hands-off method to preprocessing. So everything that you set up in the live preprocessing is basically an automatic pipeline that will take you from the raw data to particle picking. So what this means is you can, before you go and gather your data, you can enter in your settings, your parameters for the session, click send, the data or the microscope will do its thing, gather the data comes into your cluster, it goes through this pipeline, and you get at the very end some nice particles. Okay, so I've talked a bit about monitoring data quality, but what does that actually look like in our session? So you'll see at the top in the navigation pane, there's this plots tab. If you click it, it will bring up this page containing a lot of information about the quality of your tilt series. So you can see things like how the CTF estimation is going, what the estimated resolution is for your tilt series. So each of these bars in this plot represents like one tilt series in your data set. Likewise, each of the points in these graphs represents one tilt series in your data set. So you can check, how is my defocus estimation going? What's the mean defocus look like? What's the estimated resolution look like for each tilt series that I receive? And if you hover over one of these dots, it would bring up a preview image of one image from your tilt series. I'm going to demo what the data might look like. So if I go to gallery, I can see here that brings up a table of the different tilt series images that I have in my data set. You'll see it supports a large volume of data. So this one contains 1,300 different tilt series. Now, if I navigate to the tilt series tab, I can see things like the tilts, the alignment, the CTF estimation, and the reconstruction. And I can hover over the different bars in the plot on the left to change the tilted image that I'm viewing, as well as the motion trajectory. I can show all the tilts and then click on one angle to bring up a different image. Or I can click show all trajectories and bring up the estimated trajectory for all of my tilt images. I can skip forward by 100 tilt series at a time. So you'll see it's very easy to navigate these large data sets. And again, I can show all of the images in my tilt series. And as well, I can show all the trajectories for those images. Next, under the alignments tab, I can preview what the tilt image alignment looks like by clicking this play button. You'll see that everything is aligned pretty well. And again, I can navigate forward by 100 tilt series and see what happens in number 881, for example. In the CTFs tab, I can examine what the CTF profile or estimation looks like for each image individually in a tilt series. I can clear the selection and then show all the 2D plots for the images at each angle. Or I can show all the 1D plots, again, for the images at each angle. And I click an image and it will bring up the corresponding information. Again, I can navigate forwards and view the same stats for another tilt series. So lastly, if I'm picking particles in my data set, I can explore what they might look like under this reconstruction tab. So here is a sample from the HIV-1 GAG data set, where I'm picking out both the virions and the spike proteins. So I can play, and then it will go through the different stats in my 3D reconstruction and show what the picked particles look like. I can decide whether or not I want to show just the spike proteins or just the virions by clicking these two check boxes in the bottom. So you'll see at the top, there's this box for the watch option. So let's talk about that for a bit. So if I select the watch option under the tilt series tab, what this does is it essentially brings me to the most recently processed tilt series information. So I will demo this in session 2 tomorrow. But it's just keeping you on top of what's the most recent data that's been processed, how's that looking? Do I need to go and adjust any of my settings? Okay, now I'm going to switch gears slightly and talk about the resource allocations that allow us to do all of these processes on the fly. So before I do that, I'm going to define some common terms that I'm going to use in this section and that will be used in later presentations in this session as well. So the task is a Slurm job in the Slurm job array. And for each task, I'll have some number of threads allocated, and that's controlled by this threads per task parameter. So the tilt series are processed by these threads in each Slurm job, so it makes sense that the more tilts I have in a tilt series, the more threads I would want to allocate to each task. A task will also have some amount of memory associated with it. So again, the more tilts that I have in a tilt series, the more memory that I would want to allocate to that task. A good rule of thumb for memory allocation is that you want to allocate 4 times as much memory as there are threads. I'll give an example of this in one of the upcoming slides. So the wall time will control how long you want the task to run for. It's set to be like a maximum time. So let's say if I set the wall time to 1 hour, then I want the task to only run for 1 hour. After 1 hour, I want the task to be killed. Nextly, we have the CPU and GPU partition. As was mentioned earlier this morning, all nextPYP jobs can run on the CPU, but there are some external programs like RTOMO2 which require the GPUs to run, and having this different like partition specification affords us the flexibility of which programs we want to use. So like I promised, here's an example setting of how I might choose to allocate resources for, in this case, processing data from the HIV-1 GAG data set. So firstly, it's broken into 3 different chunks. So I have the resource allocation for the file transfer daemon, for the pre-processing daemon, and for the actual pre-processing jobs. The 2 daemon jobs are relatively lightweight, so you'll see there's not many resources allocated there. You'll have 1 thread for each job, 4 gigabytes for each job, so like 4 times 1 thread. And then the wall time I'm going to set for the file transfer daemon for 2 hours and for the pre-processing daemon for 5 hours. The pre-processing jobs is, I guess, where the more interesting resource allocation happens. So here I set the number of threads per task to 41 because there's 41 tilts in each tilt series. The memory per task is 41 times 4, so 164 gigabytes. And again, I set the wall time to be 2 hours to give me some time to process my data. So here's some timing statistics on typical data sets. These numbers are from running on the GPU. So you'll see, I want to highlight first that the live pre-processing supports a variety of camera types. So we support the K2, K3, and the Falcon 4. So like older ones all the way up to newer technologies. Depending on the type of data that you have, we test, so the numbers here are for the HIV-1 GAG protein data set, purified ribosomes, in situ ribosomes, and also for apoferritin. You'll see that generally the pre-processing time is pretty consistent across these data sets, regardless of like the type of particle picking that you use, the image size, and the number of frames per tilt. So it's around 5 minutes plus or minus like a minute and a half. For the HIV-1 data set, it would take around 5.5 minutes to process for each tilt series. And then for the 2 ribosome data sets, it takes around 5 minutes. And for the apoferritin one, it takes 4 minutes. So I do want to highlight here that maybe there are some other external programs, examples like RTOMO2, which might run pre-processing faster, but it's important to note here that the pre-processing here goes all the way from your raw data to your reconstruction. Other programs might not do this entire pipeline, or they might stop like somewhere in between, like for example, after CTF estimation. Okay, so now that I've introduced a bit of the timing and like how you might want to allocate resources, I'm going to explain a bit what that looks like graphically. So on the left here, I have a Slurm job in blue. Each Slurm job has some amount of memory allocated to it, which I'm showing by this orange box. And within the memory is where I store my tilt series. So there's an image of a tilt series here in the memory. Each Slurm job, like I mentioned, has some number of threads. In this case, like let's say Slurm job 1 has 5 threads. So when I tell a Slurm job to do a pre-processing task, what happens is each one of the tilts in the tilt series goes to one of these threads, and the threads will process whatever tasks I need to do the pre-processing. So this is why you want to have a number of threads equal to the number of images in your tilt series. By doing this, we allow fast feedback about the quality of your tilt images and therefore the quality of your tilt series. And the number of threads in this then will obviously affect the latency, so how fast the results are available. And like I said, you want to set the number of threads equal to the number of images in your tilt series in order to achieve the best latency to get the results as quickly as possible. So scaling up, this is the case for one tilt series. So let's say I have multiple tilt series, then I will launch n Slurm jobs where like each job processes one tilt series and the threads in each job will process images from that tilt series. Okay, so scaling up one level higher, let's say I use one of these like high throughput acquisition methods. So from the microscope, I move to one region and I collect some number of tilt series. I send those tilt series to my computing cluster. And from the cluster, I launch some number of Slurm jobs and I get the results, I process them, and I write the results to the website. Then I move my camera to another region in the microscope. I generate some more tilt series. I copy that information over to my compute network. I split those into more Slurm tasks. I do my pre-processing, I get my results, and I post them to the website. And again, for good measure, I move my camera to another location. I gather some number of tilt series. I copy that information to the cluster, and I launch jobs, and I write those updates to the website. So after I have all of my files copied over to the website, let's say I want to filter the results of my data. So I want to keep maybe some good examples. I want to keep data that came in between certain times. The filtering and exporting option will allow you to do this. So you can create different filters by giving your filter a name, adding a filter. So let's say I want to restrict the time. And I also want to filter based on CTF score. So I can do that by adjusting these sliders here, the one on the left as well as the one on the right. I can apply my filters and then you'll see the number of matches has decreased. And then I can add a third filter. So for example, let's say I want to limit by the average motion of each tilt series. So I can again adjust the slider on the left and adjust the slider on the right. Maybe tweak my parameters a bit, apply my filters, and you'll see I have like way fewer data sets than I originally started out with. I can click each of these and see what it looks like. I can save my filter and I can then load it into other tasks. So like I said, after I create these data filters, I can then export my analyzed tilt series. So this export option here will let you like select a location on your local machine where you might want to save the data that you've filtered out. Lastly, you can take your data that you've pre-processed in this live streaming session and then re-import it into an actual project in nextPYP to do downstream tasks like particle refinement or maybe change another method for particle picking. So what this might look like is I create a new project, I give it some name. So let's say import from session. I open up the session and under import data, instead of selecting tomography from raw data like we did this morning, I'm going to go ahead and pick this option tomography from session. And then it brings up a list of all the different sessions that I've run. So in this case, if I want to import data from the HIV data set, I know like I name it by the Empire number, so 10164. I can go ahead and pick that data set, click save, and it will bring up this block here. And then by running the block, I can then load in the pre-processing steps. So something important to highlight here is that when I run this block, it won't actually rerun the pre-processing. When I run it, it's just going to fetch the data that I've already pre-processed in my live session. Okay, so to give a quick summary of what I've talked about today, we've motivated why fast preprocessing and in particular live preprocessing might help us ensure data quality in a high throughput data acquisition setting. I've talked about how to create sessions, how to delete sessions, how to copy sessions, basically like how to navigate that management pane. And we've also talked about how to start, stop, smart restart, and full restart sessions. I've talked about ways that we can monitor our data pre-processing, how it's going, how things are being calculated, as well as how the like actual mechanics of files going from one place to another works, and also how the results can be live streamed to the website and how we can do that for a large volume of data. Lastly, I talked about the job settings that allow all of this fast pre-processing to happen and how we might want to allocate resources according to the size of our data. And then I talked about how we can filter results, export them to external programs, or go ahead and import them back into a project to do further downstream refinement. Okay, so I'll now take any questions that people might have.
All right, great. Thank you, Laura. That was so they have some questions actually that from earlier that are relevant to this session. So I'm going to just read them out here. So one is, are there plans to make live processing go all the way through the 3D reconstruction?
At presently, I don't think so, but like I mentioned towards the end, you can take your like pre-processing steps and import them into a project, and then from the project itself, perform refinement tasks and like do the 3D reconstruction.
Right. Yeah, I think, probably I would like to be at that point soon, but I think there's obviously going to be like, a lot of challenges, especially, I guess, unless you have like an external reference that you could use to see your refinements, which, in that case may defeat the purpose a little bit of doing like an initial reconstruction. But that's, yeah, it's a good point. And I think, I guess we're routinely doing that in single particle cryo-EM, at least for some samples. So maybe, if I can think ahead, there may be some type of samples where that could actually be, like a doable. But there may be others that are more difficult ones, which, may not be able to get 3D structures, on the fly while you're collecting the data. It'd be nice though, but all right. So there's another question here is, and maybe you addressed this, but maybe we should go over again. So for on-the-fly processing, is the raw data processed in place or is it copied into a project folder? And then what happens if the data needs to be moved to a final storage location after the data collection is done? Will the links be broken?
Right, so I think the first question was where the data exists when you're doing the live pre-processing. So, like I talked about in the sessions, like raw, when you in your session settings, you can choose either to copy your data from the microscope, so that means that it exists both at the microscope and on your like network cluster location, or you can like move the files entirely. So basically, like pick them up from the microscope location and then put them down on your cluster location. Or you can have this like third option that's not very commonly used, but like it's good for testing where you just like soft link your data. For the copy and move options, if the if it's already on your like network location in your cluster, it doesn't really matter like where the data on the microscope, like what happens to it afterwards, because your project or your session settings will like point to your like local instance of it. So for example, if you use NFS, it would be on the NFS mount. If you use the link option, depending on like whether if you delete your data, then like the link would no longer exist. So you would have to like be careful with that. And that's also why like when you delete a session, it will warn you like if you delete the session and you move your data, then your like all your data will be gone. So that's certainly something to keep in mind. I'm not sure if that also answered the second question that they had.
Yeah, I think the second part was that, if you move the data while, during data collection, and then at some point you move it to a third location, whether the links are going to be broken.
Yeah,
And
so
I
I
guess
guess
the
if
answer is probably yes.
yeah.
Yeah, so maybe one other thing to add in here is that, in some facilities, like, the data gets parked for, 90 days or whatever, some amount of time before it gets moved to some other place. Um, but even when you do that, right? So when you move the raw data physically to another location, all the metadata will still be on the nextPYP website, and you'll be able to navigate everything that was produced during data collection, right? The only thing you will not be able to do is to maybe, I guess, rerun the pre-processing, because for that you need the raw data. Um, and then in that case, you need to specify what the new location of the raw data is. But if you just wanted to go back and review the metadata for the CTF, the series alignment, particle picking, you will still be able to do that, even though the raw data would have been moved somewhere else. Okay, there are other questions. Maybe I wanted to actually clarify something. When you were talking about the timing statistics for different benchmark data sets coming from different cameras, uh, I believe you said that like something like RTOMO, for example, will stop at the 3D tomogram reconstruction. Uh, but I don't not sure if it was clear enough that these numbers that you're showing here actually include the particle picking as well, whether it's geometry based, size based, or no, network based.
Right.
Yeah.
So
So just wanted to clarify. Yeah.
the numbers here take into account like after I've have these tomogram reconstructions and then I go on and do particle picking with like one of these two different kinds of methods. The 5 minutes includes like the time it would take to do that particle picking.
Right. Okay. So there is some questions regarding resources. So what are the hardware recommendations for a powerful workstation to keep up with live on-the-fly processing for when you're collecting data, on one microscope?
Yeah, so I guess for the resource allocation, it depends on how I guess the number to keep in mind here is like the number of threads that you want to allocate for your jobs. So for each like it kind of depends on how your scheduler is set up. Like I said, optimally you would have like as many threads as you have images in your tilt series. If you have less than that, then you might have to like split your data processing into like let's say 2 rounds. If I have 41 images in my tilt series, but I only have like 20 threads per job, then I would need to process my data in 2 batches instead of in one batch. Um, Aside from like the how you allocate your jobs, the CPUs would control like I guess the number of jobs in total that you can launch. So that would restrict like the total number of tilt series that you can process at one time. So like in an ideal world, you would have as many jobs running as you have tilt series being transferred at one time. Any less than that, you would have to like I guess divide your work evenly among the resources that you have.
Right. There's a related question to that. Like if you have like a node with 32 cores, and then you're collecting two series with 41 tilts, can the tilts, I guess, be processed at once?
So 32 cores, 41 tilts, like 41 images per tilt series, I'm guessing. So you could, I guess, conceivably split up, like if each core has like multiple threads, then you can do like, I guess, 32 tilt series, and then as long as the number of threads satisfies like the suggestion that you have like one thread per tilt image, then like that would work fine. If not, then you would have to, I guess, play around with how the resources are allocated to like try and maximize the distribution of work among your cores.
Right. Yeah. So I think also, if you have more tilts than you have cores, then some cores will need to process more than one tilt,
Right,
obviously, and that will add to the running time.
right.
Great. So I think that's about. There are some more questions that we'll try to answer one by one after the session is done. But now we should transition into the last um, talk of the day, where Yi is going to talk about advanced topics and additional features. Thank you, Laura.
Thank you.